The purpose of this video is to help you understand more about torque. We already know that you can use a force to try to move something in a straight line. We will use torque to analyze forces that try to move things in a manner where they rotate around an axis. The analysis of torque is relatively simple as long as the force that is applied is perpendicular to the lever arm. And you read about that in the textbook. Torque gets complicated when, for some reason, the force cannot be applied at a 90-degree angle. So if you've ever worked with a wrench, especially underneath the hood of a car, either the wrench or where you can fit your hand make it so that you cannot apply the force that you need at a right angle to the wrench. And this makes tightening or loosening the nut more difficult. So the formulas that you can see are the formulas from the textbook, and then here and here, these are also popular versions of the formula. Can you have torque without having any motion? Well, go back to force. Can you apply a force but not have any motion? If you push hard on the wall of your house, no matter how much force you apply, probably there will never be any motion. You will not be able to move that wall. Torque works the same way. If you've ever tried to loosen a bolt that was stuck, you can apply a lot of force to the wrench, but maybe not enough force to produce enough torque to actually rotate that bolt and move it. So you can generate torque without creating any motion. And finally, torque is a vector. So torque has direction. You can turn something righty-tighty or lefty-loosey, and so the signs will determine which direction the torque is rotating the object. Here's an example of a torque problem where a 10 Newton force is being applied at a 90-degree angle to a 0.12 meter lever arm. And notice in this particular case that since the force is up, it's positive, and since the lever arm is to the left, it's negative, and that'll be one of the ways that we figure out in this problem that in the end there will be a negative torque. Another thing about this problem is that we have torque equals the lever arm times the force times the sine of theta, but we know in this problem that we don't really need to use the sine of theta because the sine of 90 degrees is 1, and that won't change the answer. So to do this problem, we would have our lever arm times our force times the sine of 90, although we know that we're writing this down for no reason, it won't change our answer. And when we multiply those, we'll find out that our torque is 1.2 Newton meters. Now when we take a look at our signs, we had a negative lever arm and a positive force, and when we multiply those together, that will make our torque negative 1.2 Newton meters. In this example, we have the same lever arm, we have the same force, but our ability to produce torque and turn the bolt has been reduced because of the angle. The force is no longer at a 90-degree angle to the lever arm. Now the force is at a 30-degree angle to the lever arm. So using the instructions that are in the textbook, if we extend the line of the force and then we go to the axis of rotation, we need to draw a line from the axis of rotation to the line of force, and that line needs to make a 90-degree angle. So it would look something like that. And so in this problem, the amount of torque that we're going to be able to generate is not going to be the same as if we had a 0.12 meter lever arm, because the force is at an angle. Our lever arm will only be as effective as a lever arm with the length of this new blue line. And so if we can find the length of that blue line, then we will know the effective length of our lever arm. And so if we start out with our 30-degree reference angle, this is our hypotenuse, this is our adjacent side, this is our opposite. So in order to determine the length of the opposite side, we're going to use sine. So we can calculate this side by doing the sine of 30 equals the opposite over the hypotenuse. And when we do those calculations, we find out that x is equal to negative 0.06. So as we're learning how to do these problems, what we just found out is that this right here represents the actual length of our effective lever arm. Because of the angle, we no longer have the effect of a wrench with a length of 0.12 meters. Now we only have the effect of a wrench with a length of 0.06 meters. So we will have less torque because we have a lever arm that's less effective. So we could solve this problem right now without using this fancy formula. We could just figure out the torque by taking our effective lever arm and multiplying it by our force, and our torque would be 0.6 Newton meters. An easier way to get this answer with less thinking, and it works on this problem, is just to plug our numbers into this formula. Notice I'm going to erase the perpendicular, and I'm going to put in the lever arm, which is negative 0.12, and I'm going to put in the force, which is 10 newtons, and I'm going to put in the sine of 30 degrees. And when we do those calculations, the answer will come out to 0.6 Newton meters, the same answer that we got before. And before we can finish this problem, we have to make sure that the signs are done correctly. So our torque is negative 0.6 Newton meters. All right, in this example, for whatever reason, again, the torque or the force cannot be applied at a 90-degree angle. So using the method that the textbook suggests, we are going to extend the line of the force. Then we're going to go to the axis of rotation, and we're going to draw a line from the axis of rotation to the line of the force, and that line is going to be perpendicular. So this is our new effective lever arm, shorter than our actual lever arm because the force is being applied at an angle. Now in this problem, something comes up that often confuses students. Which angle do you use when you're calculating the torque? Well, as you can see, the 150 degrees did not end up to be one of the three angles of our right triangle. So if we put our protractor right here, 180 degrees minus the 150 degrees means that this angle right here is a 30-degree angle. And that's why we draw the triangle by drawing the line from the axis of rotation to the line of the force. Is that way we know which triangle we're talking about and we can figure out which angle we're talking about. So there's two things that we could do right now. I could just use trigonometry to find the length of our new lever arm, or I could just plug these numbers into our torque formula. Since I know that I drew the picture correctly, I'm just going to put the numbers into the formula and find out what the torque is. So for this problem, the actual lever arm is 0.12. For this problem, the force that's applied is 10 newtons. And for this problem, the force is applied at a 30-degree angle. And so when we do the calculations, we will get a torque of 0.6 Newton meters. And because our lever arm is negative, our answer for our torque will be negative. And if you're paying attention, you realize that that's the same answer that we got on the last problem. In this problem, we're back to a perpendicular force. And I'm just going to show you, using the textbook method, how this fits into the pattern with the rest of the problems. If I extend the line of force, and then I go to the axis of rotation, and I draw a line from the axis of rotation to the line of force, that makes a 90-degree angle. That is the blue line that's already there. So I can't draw a different triangle with and find out an angle because there is no angle in this problem. It's a perpendicular force. So on this problem, it's exactly like the very first example that I did, only half of the force is being applied. It's only a 5 Newton force instead of a 10 Newton force. So for this problem, we have negative 0.12 times a 5 Newton force, and then I'm not even going to spend the time to write down the sign of 90 degrees because I already know that it's 1. So that comes out to negative 0.6 Newton meters, which is exactly half of the torque from the very first problem, which makes sense because it's the same lever arm, but only half of the force. In this example, we're back to applying a 10 Newton force. We're still applying it at a 90-degree angle, but now instead of grabbing the wrench at the end, we're grabbing the wrench more in the middle. So our lever arm is only 0.06 meters long. So when we go to find the torque, we're going to go torque equals lever arm times force times the sine of 90, which we know is 1. So our torque on this problem is going to be negative 0.6 Newton meters. Now you should notice something interesting. The last 4 problems that we did all have the same torque, negative 0.6 Newton meters. So here's something to think about. If you have to apply a 10 Newton force and you're using a 0.12 meter wrench, you'll generate 0.6 Newton meters of torque. But if you can just change the angle so that when you're either pushing or pulling on that wrench, you're pulling at a 90-degree angle, you can generate the same amount of torque, but with only half of the force. So the same would apply to this middle example here. If you get at a weird 150-degree angle and you're pulling on that thing or pushing on it with a 10 Newton force, you're only going to generate 0.6 Newton meters of torque. But if you could get that thing at a 90-degree angle and you could push or pull on it with a perpendicular force, you could generate the same torque with only half of the force. And then finally, over here in the example that we just did, if you have a wrench and you grab it in the middle, so in this particular case, your lever arm is only 0.06 meters, that 10 newtons of force is only going to generate 0.6 Newton meters of torque. And if you could grab the end of the wrench, you would do the very first example that we did, and you would generate twice the torque just by moving your hand to the end of the wrench. In this example, I'm going to do the same problem 2 different ways and get the same answer. The first way is the method suggested by the textbook. you extend the line of the force, you go to the axis of rotation, you draw a line from the axis of rotation to the line of the force that makes a 90-degree angle. And the reason you draw the triangle is so that you can make sure that you're using the right angle in the formula. So in our problem right now, we can see that this side right here, which is our effective lever arm, in this problem, we will not have the effect of a 0.5 meter lever arm. We'll have less effect because of the angle. And so we're going to adjust the lever arm that we put into the formula in order to account for the angle. And so if we did that, we could figure this out by using the sine of 45 equals the opposite over the hypotenuse. And in that way, we could calculate what the effective lever arm was. And once we did that, we wouldn't need to use the sine of theta in the formula. And so the answer to this problem is going to be that the torque is equal to, I'm just going to put in the whole lever arm, times the force, which is 20 newtons, times the sine of 45. And what I'm hoping is that this stuff up here will help you realize why the sine of 45 is in the problem. And so when we type that in, we should get a torque of negative 7.07 Newton meters. All right, a second way of doing the same exact problem is to adjust the force to account for the 45-degree angle. And this is familiar because this is just like drawing a free body diagram. So in this problem, that red force vector is at a 45-degree angle. So some of that force is being used to push the bolt to the right, and some of that force is being used to push the wrench up. Obviously, the effective force in this problem is the force that's pushing the wrench up. So if we figure out what this line is right there, that's the actual amount of force that we're going to be applying to the wrench. It's not going to be 20 newtons because of the 45-degree angle. So if we wanted to figure out how long this line was, we could do the sine of 45 equals the opposite over the hypotenuse. And so you can see that again, we'll have 20 times the sine of 45 times the lever arm. So when we come down here, our torque will be negative 0.5 meters times the force, which is 20 newtons. But then the sine of 45 adjusts our force so that it's the actual amount of force that we'll be using in this problem, which is reduced from the 20 because of the angle. And so you can see in both problems, we're multiplying the exact same numbers together. Some students find it much easier to do the problem the way I'm doing it now because they're familiar with free body diagrams. So our answer will come out to exactly the same answer. Finally, on this last example, I'm going to do the problem that I think is the best way to do the problem. Many students get confused by which angle to use, and so I think it's better to do the problem and figure out either the adjusted lever arm or the adjusted force separately, and then just forget about the sine of theta in the formula. Take care of that while you're drawing the picture. So in the example on the left, we are going to do the problem the way the textbook suggests. We're going to extend the line of force. Then we're going to go to our axis of rotation, draw a line to the line of force that's perpendicular. So that's going to look like that. So in this problem, you can see that our 130 degrees isn't inside of that triangle. So if we put our protractor right here, 130 degrees minus 180 degrees is 50 degrees. So the angle inside of our triangle is actually 50 degrees. And although our lever arm has a length of 0.75 meters, we will not get that full effect because of the angle. So this is our actual effective lever arm. That blue line is shorter than our lever arm. So we're going to figure out the value or the magnitude of that vector right there. So in this problem, this is our reference angle, that's our adjacent side, that's our hypotenuse, and this is our opposite side. So I can find the side that I want by using the sine of 50 equals the opposite side, which I'm looking for, over the hypotenuse, which is 0.75. Notice that this time the wrench is facing the other direction, so our lever arm is positive, but our force is pointing down, so our force is going to be negative. So we're still going to have a negative torque. When I do the calculations, I find out that X is 0.5745. So what we just found out is, although we actually have a wrench that's 0.75 meters long, because of the angle, the torque that we're going to generate is going to be the same as if our wrench was only 0.57 meters long. So now that I know my effective lever arm, my torque is going to be my effective lever arm. So that's 0.5745 times my force, which is negative 27 newtons. And when I multiply those two numbers together, I will know the torque. So the torque is negative 15.5124 Newton meters. And finally, I'm going to do the problem like I'm using a free body diagram. So in this problem, part of that negative 27 Newton force is pulling the wrench in this direction, and part of it is pulling the wrench in this direction. Obviously, this is the one that's going to be the effective force. That's the one that is going to rotate the bolt. So if we can figure out what that vector's magnitude is and put that into our formula, we won't need to use the sine theta part of the problem. Now, one thing that you can notice, the complete 130 degree angle is not inside our triangle. So we want to find this angle right here, and this is 90 degrees. So 130 minus 90 is going to give us 40 degrees. So the angle that we're going to use to make this calculation is a 40 degree angle. And if that's our reference angle, this is our hypotenuse, this is our opposite, and this is our adjacent. So this is where the problem involves thinking instead of just plugging numbers into the formula. Instead of using the sine this time, we're going to use the cosine. So if I want to find this side, I'm going to go the cosine of 40 degrees equals the adjacent over the hypotenuse. So when I do the calculations, I get negative 20.6832. So because of the angle, what was a 27 Newton force has been reduced, and now it's only a 20.68 Newton force. So the angle has affected the amount of torque, and it's changed the effective force in the problem. So now when I go to calculate the torque, I'm going to take the lever arm, which is 0.75, times the effective force. Not the full force of negative 27 newtons, but the effective force of negative 20.6832 newtons. And when I multiply, my answer is negative 15.5124 Newton meters. The same exact answer that I got when I did the problem using the other method.